tools to help people develop simulations, but then we also use our own tools. So a lot of this presentation is about how we develop the tools. You heard Paul talk about a great use case, which is flight training for AR/VR technology. But those use case applications have to come from someplace. They have to be developed as software applications. So this afternoon, I'm going to talk to you about lessons learned from the many systems that we've built, similar to the ones that Paul was talking about, and the importance of being able to do that efficiently and quickly. And the way we do that is through a database approach. We use data management tools and processes and people to efficiently develop these applications. So the outline for the presentation, I'm going to talk a little bit about some of the challenges in building virtual simulations, talk about the data that they need, and then our approaches for managing that data. So first is virtual simulation development challenges. These AR and VR applications typically have a simulation running beneath them. Many of the features that these applications have are built on top of those simulations. So for example, in things like maintenance trainers, we monitor the students' performance and their activity and their interactions. So those provide instructional support features on top of the simulation. So I'm going to use virtual maintenance trainers as a running example for the presentation as one type of AR, VR, or desktop simulation. So whether you're building your application yourself or outsourcing it to a company like DiSTI to build it for you, it's important to understand how these things get built. And a lot of organizations we're finding now, because of the availability of tools, are starting to do these development efforts themselves. They're not having to rely on an outside group. The other trend or mega trend is that game engines have evolved to such a point where you can quickly and easily take those off-the-shelf tools and build these applications. I was actually at a student seminar this week at the University of Central Florida where they brought in high school students who were using things like Unity and Unreal 4 to create applications that were really impressive, and it was neat to see how even a high schooler can build these applications now. You don't need a large team of experts to do it for you any longer when you're developing something simple. But that development effort, even with the game engine, is very labor intensive. And we're finding that even if you could find the people, it takes a lot of people to develop these applications. So you need to be able to do it efficiently. And you need to build quality products as you're doing it quickly and with less cost. So Paul had this image on his slide as well. My point here is that as we've evolved in the development of simulations, we're not just focused on the technology anymore. It's not about just integrating a head-mounted display with software. It's now about focusing on what is the problem you're trying to solve. Are you trying to teach someone to fly an aircraft? Are you trying to, as an architect, to help someone visualize what their new home is going to be? The focus is moving toward the content, the application, the problem you're trying to solve. So a lot of that has to do with data and content being king. So the thing with data and content is that it evolves. Paul was talking about aircraft. As the aircraft get modified through the years, you need to update your training. If your applications are very data-driven, it's easier to update your application. So when I'm talking about data, there's really two major types of data that are involved in developing these applications. One is the initial development of the application, and the other is the real-time runtime performance of the application on the various platforms that you're deploying it to. So that data that you're using to both build it and run it comes in different kinds of flavors, and people talk about data, information, knowledge, and wisdom. But the important thing about the data is you want it to be accurate. So we talked about the fidelity of simulations. You want them to accurately represent that thing that you're trying to train. So for example, in the flight training situation, you want it to feel like the real aircraft's going to feel, so you don't introduce negative training. You also want it to be sufficiently detailed. You don't want things to be too fuzzy. You want them to be close enough to the real world that the person gets the kinds of training that they need. The data needs to be integrated So things like what you see in the environment needs to be tied to a simulation variable so that the simulation that's running is visualized correctly in what the student is seeing or the user is seeing. You also want to make sure all that data is traceable for a couple different reasons. One is verification, validation, and accreditation. So you want to be able to make sure that you've got that link of information through the process so you can trace it back to authoritative data sources. And as I mentioned with concurrency, you also want to be able to update the application easily, so that traceability is important. If you want to know if the throttle changed on your aircraft, what does that affect in your application? So if you have that traceability, you're able to figure that out and focus in on what you need to update. You also need, for these applications, for them, the data to be simple enough to run in real time. The rendering has come a long ways. Right now with PCs and game cards, you can quickly render things, but it's not the same as rendering out to video or to a movie where you've got non-real-time performance considerations. So that's the data that you need for these applications and why it's important. So what kinds of data are we talking about? This is a diagram popularized by Robert Sargent. And what it tries to do is separate out the problem entity or the system that you're trying to represent from a conceptual model of that real-world space, and then the computerized model or the application that results from that development effort. And what he tries to show with the arrows is all the linkages for the validation and verification. So as you perform analysis and modeling to come up with your conceptual model, you're able to do validation to make sure it accurately represents the problem entity. And as you implement it into an application, you're able to do verification or testing to make sure that you correctly implemented it in the application. And then once you have that application, you're able to do some experimentation or testing, especially with subject matter experts, to make sure they get the sense that it accurately represents the real world. So I'm going to step through this in a clockwise manner, talking about how that data is important for development. But first, one example is from a virtual maintenance trainer we developed for a helicopter system, the UH-72A. So we have the real world was the helicopter. We developed conceptual models of that and then wound up creating a virtual maintenance trainer, which has 12 student stations and an instructor station that's used on a daily basis now for them to practice performing maintenance tasks on a helicopter. So the real world, it consists of platforms and objects, so real things like a helicopter, but it also includes things like procedures. Often the original equipment manufacturers or others will come up with procedures, whether they're operator or maintenance procedures, that describe how to interact with those platforms or objects. And as we try and get our arms around that real world, we gather or harvest all the information about that subject platform. One of the first things we typically do, especially for maintenance trainers, is a procedure analysis. So we start off with tasks to be trained, because that really scopes what your applications can provide. So for example, in Paul's flight example, he was talking about a particular task that they were trying to train them on, like formation and flying. So based on the task you're trying to train, that helps you identify which procedures you need to analyze. And once you know which procedures you're analyzing, as you go through those, you can identify which equipment to model. When you're building these simulations, you don't want to model the whole thing. It could take too much time and too much money. You want to focus in on just the pieces you need for your particular application. So going back to the UH-72 example, we had about 40 tasks to be trained. That wound up leading us to about 250 procedures that came from the helicopter and engine manufacturers. And we wound up with about 4,000 objects in our simulation because of that. So those were the 4,000 objects needed to support the 250 procedures, which were defined or scoped by the 40 tasks to be trained. Once you know the procedures and the subsystems, it forms what we call an envelope. So this helps us scope the effort based on the procedures as columns and the subsystems as rows. It sort of forms an encapsulating scope for what you need to build into your simulation. The good news is that as you add more procedures and more subsystems, there's a lot of overlap. so the costs don't go up linearly as you add more content. The first step we do is to harvest information about the real world. And we do this in several ways. Authoritative data sources are key. So I mentioned the OEM procedures. There's often technical drawings, and in some cases there's CAD data, but there's not always CAD data. So often we're going out with scanners or cameras and collecting information about the equipment. And we bring that back, and our modelers create the 3D models from those sources. If we do have the CAD data, we're able to convert the CAD data into the 3D models that we need as well. But often we have to simplify them down so that we can render them in real time. We do knowledge elicitation sessions with subject matter experts. It's very important that our engineers who aren't experts on things like aircraft or helicopters talk to the experts and make sure they understand what they're implementing in the simulation. Another thing we often do in the photo shoots is to gather scan data. That gives you point clouds that the artist can then use as reference as they're building the 3D models. So the first phase of this going around the circle is the analysis and modeling. And this is where we're distilling all that real world information into models. And there's a couple activities that are involved. One is knowledge engineering, and then the other is creating the 3D models. So in the knowledge engineering phase, we're trying to take a lot of this information and encode it into files or into models to help us migrate that information into the simulation. And one of the key things for the virtual model is to use that CAD data I was talking about, or the photos, to create the textured 3D models. So this is an example. On the left is a photo we took when we were doing the photo shoot, and on the right is a screenshot from the application that comes out of the trainer. So you see how similar and realistic those models can be, even though we weren't using CAD data, we were using scans and photos. So a lot of the effort in building these simulations goes into this aspect of the data, the textured 3D models. And there are a lot of off-the-shelf tools for things like that, like 3D Studio Max or Maya. So the next part of going around the circle is the conceptual models. This is where we take the information about the real world, we distill it down and represent it in a neutral type format so that we can validate that against the real world using subject matter experts, and that we can then migrate that through the development process into the final product. So these conceptual models are encoded into a variety of data formats. You might have things like state charts. A lot of these simulations have cause and effect simulations. So state transition diagrams are often used to describe the behaviors for those. Things like procedures are often migrated into Excel workbooks because you have lists of steps and procedures. We sometimes use ontologies to represent the semantics of the relationships between things. So something like a 3-position switch is a switch. So we know that certain things that a switch has, like state, are also found in things like 3-position switches. And I mentioned graphical representations using those modeling tools. So once we have those conceptual models, we're able to use those to implement. This is where we create software code that we don't already have off the shelf from things like game engines. And we also tailor game engine data. For example, the Unity game engine has C# that it uses for scripts. So the software engineers are able to go into the game engine and using Microsoft Visual Studio, create those behaviors for those objects. So this whole implementation stage is to prepare the data so that you can create the executables of your software. So some of the models and content, the 3D models are used by the rendering engine like Unity. Behavior models are often used by a simulation engine that processes those scripts or those state transition diagrams. And then lesson or scenario data is used by software like procedure monitors. Procedure monitors provide features like intelligent tutoring systems, where you can comparing the student's actions to the ideal student actions, and you're able to give feedback to the student about where they're deviating from the preferred approach. So once you get these implemented files, it's important for a simulation to balance the performance of that data for real-time rendering to the quality and the detail that you'd like to present in the simulation, since these are real-time. So some examples of the different kinds of data. You've got scenarios and lessons. Those are things, as I mentioned, the intelligent tutoring system would use as it's comparing your performance. Virtual environment initial conditions are things like being able to set up a rainy day for your flight simulator. The 3D models are an evolution of the 3D Studio Max files. Object behaviors are things like doors opening and closing. And you also need things like constraints. For example, you don't want a door to close if there's something plugged into a socket that would block that door. You can sort of think of code and scripts as data, although we typically think of code as being different from data. It's really just bytes again. And then there's configuration data, hardware setup. So for example, in your classroom, if you have a dual monitor system, so a single monitor system that can be read at runtime by the software, and you can tailor your deployment based on that information. We also have persistent ad hoc data. This is information that's collected in the process of executing your simulation. So you might want to be able to pause the simulation, go have lunch, and come back to it. So you want the ability to save out that information, similar to how you would represent initial conditions. We also have things like after action reviews. So you want to collect a lot of information as the student is performing the training so that afterwards an instructor can show them what they did right and what they did wrong. We do that through logging data. We also capture video a lot of times so that the instructor can play back the video and show the class what happened in the simulation. So game engines create the requirement to store certain types of information. So this is a screenshot from Unity where we've got a tank model and we've got the different parts of the tank, from the wheels to the suspension to the tracks and the turret. So all of that forms part of this object hierarchy, and each of those items has parameters associated with them. So it's important that we have all of this data that's needed to drive what the game engine needs to be able to render it and interact with the student when they're executing the simulation. Now, some of the data management is within the game, but others is outside of the game engine. So when you have all of these representations from the real world to the conceptual model to the data files, it's important that they're all linked together so that you can perform the traceability objectives that I was talking about. So lastly, if that's the data that we want to manage, there are different approaches to managing that data. We talk about the solution in terms of people, processes, and technology. So on the people side, it's typically an interdisciplinary team. It's important to have subject matter experts that know the domain, artists that can model the representation, engineers that can implement the solution, and the people that can test or validate it. On the process side, we really encourage the use of standards. I talked about the knowledge elicitation, conceptual modeling. Configuration management is also very important so that you track all the changes as data evolves over time. But the key here for process is that it's supported by tools. You really need tools to support your process. So that's where the technology side comes in. You need features in the tools to satisfy the data requirements, both during development and support at runtime. And there are two major types of tools. There's the content editing tools and the content management tools. So on the editing side, we talked about 3D Studio Max and the game engines. Those are examples of content editing. And then on the content management side, things like configuration management tools. There are also things like metadata taggers. So we use Adobe Bridge when we do a photo shoot to associate metadata with all those photos so that the developers can find what they need. So at DiSTI, we have a set of tools that we use for our data management. The requirements analyzer tool helps us do the procedure analysis where we're parsing PDF files of the OEM procedures to pull out those nouns and verbs so that the engineers know what they need to implement. We have the fidelity matrix editor that helps us edit the database of content. Then we need to link what the artist developed in 3D Studio Max to those object representations. So we use something called MaxLink. And then we use our VE Builder tool to collect all that data together and turn the crank and export the executable of the file that we need to run as the trainer. And then we have some automated tools for testing those executables. So the centerpiece of that tool set is the fidelity matrix. That's where all the data comes together in a database. It's a relational database that takes all of the pieces, parts, ties them all together so that those other tools can leverage that data and support the runtime. So the primary takeaways here is that you want to focus on the data to support the development and execution process, and you want to be very intentional about how you manage that data so that the development effort is efficient and as low cost as possible, and that you have tools, automated tools to help you do that data management throughout the development lifecycle.